Okay, this topic is about force and a current carrying conductor in a magnetic field. Okay, we have seen before that when a charged particle is moving in a uniform magnetic field, then the charged particle always experience a magnetic force. Okay, so as you know that when a current is passing through a conductor, then the free electrons in the conductors are moving. So as these free electrons are constrained inside a conductor only, so it means here that all the free electrons which are present inside the conductors are moving. So when these moving free electrons are placed in a magnetic field, then these free electrons will experience a magnetic force. Okay. Suppose we will consider here as I is the current which is passing through the conductor, and let's say E is the charge of each electron, and each electrons they are drifted, you know, with a velocity known as drift velocity. And let's say small n here is the electron density, which means the electron present per unit volume of a given conductor. L is the length of the conductor. Okay, so these are our consideration in this case. Now, as you can see in this figure, this conductor is placed right in the magnetic field at an angle theta, and this conductor it carries a current I in this direction. So it means each free electrons will be drifted right with a drift velocity, let's say in this direction. Okay, now because electrons is a charged particle, so when a conductor carrying current is placed in a magnetic field, it means you are exposing the electrons to the magnetic field. So therefore the magnetic force which will experienced by each electron in this case, it will obey the equation like F is equals to QVB sine theta. Okay, but instead of Q the charge is E, and instead of this V, which is the velocity of the charge, so now the velocity of these charged particles, which mean the electrons, it is Vd. Okay, so this is the magnetic force which is experienced by each electron when placed in a uniform magnetic field B. This is not Fe, this is F. Okay, we usually write Fm as magnetic force. Okay, so now what will be the net force which is acting over the entire length of the conductor? If the force on each electrons is this much, then how many electrons are present over the entire length of the conductor? Okay, because we have imagined here that n is the electron density, which means the electrons present per unit volume. So when there are n number of electrons in a unit volume, then the total number of electrons over the entire volume of the conductor will be, you know, number of electrons per unit volume times the volume of the conductor, which means if this is my area A, then area into length will be the volume of the conductor. So now this number of electrons into the volume will give you the total number of electrons. So if each electron is experiencing a magnetic force this much, then this much number of electrons, I can see the total magnetic force experienced by the conductor will be F is equals to this number of electrons times the force due to each electrons. Okay, or this total force which is acting on a conductor carrying current, it is equals to NAL. Instead of Fm, I will write EVD B sine theta. Okay, or I will write this as and EAVD. I will arrange first like this, and then I will write LB sine theta. So this is just the rearrangement of the term, but if you look carefully at these, at this term inside bracket, we have NEAVD. So what is this NEAVD? If you remember in the chapter 3 about electric current, this NEAVD, it is the electric current I. So instead of NEAVD, I will write I, and then I'll have L, B, and then sine theta. Okay. Now, this is the magnitude of the magnetic force which is experienced by a conductor carrying current placed in a uniform magnetic field. Okay. Please note down here that this theta, it is the angle between the length and BL. Now this is my length, it is acting along this direction, and this is B. So this angle, it is the angle between L and B. Okay. In vector form, this magnetic force F can't be written as I L cross B. So this is the vector form of the magnetic force due to a current carrying conductor when placed in a magnetic field at an angle theta. Okay. After this, let us discuss about some special cases. And the first case is when theta is equals to 0 degree or 180 degree. So looking at equation 1, when theta is equals to 0 degree, then your F is equals to ILB sine 0 degree. So we know sine 0 is 0, so everything will be 0. Again, when theta is equals to 180 degree, equation 1 becomes ILB sine 180 degree. Sine 180 is 0, so 0 times ILB will be 0. Okay, so what does it mean? It means that if the conductor, it is arranged parallel to the magnetic field, right? So when there is a current passing through the conductor, in that case, right, the magnetic force acting on the conductor will be 0. Or in other words, you can say that when the conductor carrying current is placed parallel or anti-parallel to the magnetic field, then the conductor will not experience any magnetic force due to these reasons. Okay, the second case is when theta is equals to 90 degree. So when theta is equals to 90 degree, your equation 1 becomes F is equals to ILB sine 90 degree. And you know sine 90 is equals to 1. So 1 times ILB will be equals to ILB. So F here is equals to ILB, which means it is a non-zero. So if it is non-zero, I can say that this force here, it is maximum. Okay, so this means that when the conductor is held perpendicular to the magnetic field, then that conductor will experience a maximum magnetic force, and the value of the maximum magnetic force is equals to ILB.